So moving forward in this video we are going to discuss a very simple problem related to square root decomposition, and you can find the problem link over here. It's dynamic range sum queries, and the problem says that you're given an integers and you have to process q queries. The query can be of two types. I either update the value at any given position k to u, and what is the sum of values in the range of a to b, right? So how to solve this problem, and I will tell few things regarding this. So let me first of all copy this problem statement, and let me make a separate section over here. So this is nothing but, okay, let's not do that, we can simply paste it over here. Okay, so now the problem is dynamic range sum queries, and so you have to perform two types of queries. So this is query 1 and this is query 2. The input is that in each case you have to print the result of each type of query 2. So there is no need to print anything if it is q1, just update it at any given position. And the constraints are the number of elements and the number of queries will be up to 10 to the power 5. All right, and you have to answer 10 to the power 5 queries, right? So this is now very obvious that each query can be answered in at max. We will see about the complexity later, let's not worry about that now. Okay, but obviously each query cannot take order of n time, right? So order of n time cannot, it is, each query cannot take this much time, because order of n will simply mean 10 to the power 5, and if there are 10 to the power 5 queries, then this will simply go to 10 to the power 10 and this will TLE. So we need something which is better. All right, so we need something which is better. So dynamic range sum queries, this particular problem statement can be solved using various techniques like segmentary and whatnot. But in today's video, we are going to focus especially on the square root decomposition approach. All right, so let's go to the some sample example to understand the problem statement better. And in this case, we are going to talk about this particular example, which is given in the sample input. Okay, so let's talk about this, that we have an array. All right, so this is our array and we are given four queries. In the first query we go to the index number 2 and we tell that update the okay, in not index number 2, the first query is of type 2, which simply means that give me the sum from range 1 to range 4. So range 1 to range 4 will simply mean from starting from here 1 2 3 4 and ending over here. So this will give me the sum of 12. Okay, so this is one based indexing. So if I start from here and end it here, then this will be 5 plus 4 9 plus 2 11 plus 3 14. So the output is 14. So indexing is one based. All right, so next this is also simple, this is also simple. The problem is when we update an element, then how we will compute the following upcoming results, right? So this is where we call this particular thing as online, right? So there are two types of query related problems. One is offline, second is online. Now online means that whenever we update any particular element in between queries, right? If there is an update query, then we call that particular problem statement as online, which means that we cannot pre-store all the queries and run results based on certain approaches. We have to follow the sequential manner, right? Which means that query 1 has to be processed and computed first before answering query 2. All right, because query 2 can update an element and therefore subsequent results for the subsequent queries will differ depending on what the update is. So this is online approach. Alright, so now let's talk about how to solve this particular problem statement in using square root decomposition. So as I said before, like this particular problem, in this particular problem, what we can do is we can write down the array 3, 2, 4, 5, 1, 1, 5, 3, and we know that n is equal to 8. So what will be the value of square root of n? Square root of n will be nothing but 2. All right. So how many elements are we going to have in each block if I want to divide this particular array into block? So let's figure that out. So we have already seen that 8 divided by 2 is 4, which means that there will be 4 blocks, right? So this will be block 1, this will be block 2, this will be block 3, and this will be block 4. Let's index our block like this: 0, 1, 2, 3. So we have 4 blocks. Now the point is, if I want to compute the range sum, let's say starting from 1 to 4, I want to first of all figure out that there will be each block can be of two type, right? Can be actually of three type, right? So let us say that I am talking about any block B, then this block B can play three kind of roles in for answering each type of query, right? Either it will not be present at all, so it's not included in the current answer. So for example, if I talk from 1 to 4, then I know that I want answer from here up to here. So if I talk about the role of block 2 and block 3 in answering query 1, then they are not included in the answer at all, right? The second kind of role that a block can play is that it will be included completely. All right. So included completely. Like so included completely, which means that let us assume that I want to compute from this particular point to this particular point. Then what is the role of block 1 and block 2 in answering this query? It will be included completely. Alright, so this is the second type of role that a block can play. Now the last role that a block can play is it will be partially included, right? Of you can say included partially, IP. So let us look at the very first query. From answering 1 to 4, what is the role that these particular blocks are playing? Block number 0 and 1. Okay, so they are playing the role of included completely. So this is not a good example. So let us come back to our original, that is starting from this index up to this index. If I want to compute the query, what is the query? To compute the sum of all the elements present from this particular index to this particular index. Alright, so in this particular case, block number 0, block number 1 and block number 2, these blocks are included completely, but block number 3 is included only partially. Why? Because over here we are not including the answer for the entire block. We have to include the answer only to a certain point. Okay, so now there can be two kind of there can be two kind of things possible, right? So let us say that come to any particular block. As I discussed three roles, out of which this is not a point of discussion. IC and IP are point of discussion. Okay, so if I already know the answer of the sum which is present in this particular block, right? If I already know that the sum of this particular block is X, then for each query do I need to iterate over all its elements to compute the sum? Obviously no. We can, if I know X, I can directly add X to my answer of that particular query, which means that I saved some iterations. How many iterations do I saved? If the block size is S, then I saved S iterations. Alright, and in similar fashion, how its iterations will I save if there are, let us say, C number of IC number of let's say let's forget about that. So let's not talk about iterations right now. Let's go step by step. All right. So yeah, if I know the answer of this particular block, then I can directly add it to my answer without actually going through the block, right? I can add it to my answer directly. Now the second point is, if I do not know the answer of this block, then I have to go through each element in this block and add it up. Of course, yes, I will need to do that. Okay, so this is one thing, but is it required to do this as a part of any query? Can I pre-process this? Of course, I can pre-process this. So let us say that my block right now has two elements. Let us say that the elements are 5 and 3. And before actually computing the answer for any query, I pre-computed the sum of all the elements in each block. So I pre-computed that the block sum or the sum of this particular block is 8. Okay, then what happens is, let us say that there is an update which is coming for this particular block, and now this element 5 is changed to element 2. So what will be the impact on this particular block for this particular point update? We call this as a point update because we are only updating a single index. So for this particular point update, what my current sum is, this is 8. So I have to subtract 5 because it is no longer a part of my block. And then I have to add 2 because it is now the new element which is present instead of 5. So my block sum will get updated. Alright. So do I need to iterate over each and every element in each and every query for doing the point update and updating the sum correct with the correct value for each block? No. Why? Because this can be done in order of one time, because the element which is present at the given index can be accessed in order of one time. The block sum, the previous block sum, can be accessed in order of one time, and therefore the update can be made in order of one time. All right, so this means that whenever we come to any kind of query of type 2, we can already safely assume that the block sum is already up to date for each and every block. So we do not have to worry about the stale or a wrong block sum. Okay, so we already have the block sum which is updated and correct. And so to quickly summarize the Q1 type, what we can say that for Q1 we can simply say the previous block sum minus the current value plus the new value will be equal to the new block sum, right? So this is nothing but just one equation that will help us a lot. So this is nothing but the type that this is the action that we need to do in order to update the block sum for after each and every update query. Okay, so now coming to the query of type 2. So in query type 2 we already identified the three different kind of roles that each block can play. Okay, so now let us answer query wherein we have to start from point 3, like from this point, and end up to this point. Okay, so we first of all, let us come down and make some more space for this. So for query 2, let us say that we are given two indexes, the left and the right. Okay, so for the corresponding index we can find out the block index, because as we said earlier that we can give each block an index. So this 0 1 2 3 is nothing but the block index. So we will figure out what is the block index. So we can say that BL is and BR are the block indices for these two particular index. So now all the blocks which reside between BL and BR, so be it BL plus 1 and up to BR minus 1, so all these blocks will play what kind of role? It is very clear that BL plus 1 to BR minus 1 blocks will be added instantly, because we just have to figure out what is the sum, right? And to know that, if we already know the block sum for each block, then I just need to add them up. So this operation will require how many steps? If I want to make a linear loop, then in the worst possible case, I would need to end up adding all these blocks. So how many blocks are there? So let us say that we divide our entire array into k blocks, right? As we did in the previous video. If you have not watched that, so we are going to divide our entire array into k blocks, right? So over here we are coming to this particular part of why this equation was important, as I discussed it in the previous lecture. So if I divide my entire array into k blocks, then in the worst case, to answer a single query q2 of type 2, I might need to iterate up to the k number of blocks. If I have, then I might need k iterations because I want to compute the sum. All right, and now it might be possible, like we discussed over here in this case, that we end up getting something like this, wherein if I want to compute the answer from 3 to 5, we will have to make the additions of block, like we will need to add this block sum, we will need to add this block sum. All right, so there will be like coming down below we will have BL, right? And then we will have to iterate and up to BR. So over here we are doing a linear iteration, but in BL and in BR we do not need to add all the elements, right? So if I talk zoom in, let me zoom on BL. So let us say that this is BL block. Okay, so let us say that this BL block is are having elements, right? Element can be something like elements will have, there are certain number of elements, right? So and but we will need to add up from somewhere, starting from some point. Okay, so let us say that we need to only add these elements and all the further elements which lie in this particular region, and then let me zoom BR. So if I zoom BR over here, then BR will look something like this, and there will be elements, but we only need to add up to certain elements over here. So this particular part we need to make a linear loop to add only this element, because BL knows the sum of this entire block, but we need only this particular portion, so we will need to add them up linearly. Okay, so we will make a linear for loop to add the elements from starting from this point up to the end of this block, and similarly starting from this block entrance up to the index which is provided to us, we need to linearly add them up. So how much is the time complexity to linearly add this up and add this up? So in the worst case, it might happen that we need to end up the entire block. We need to add up the entire block. Let's say just we leave one element and we need to end up adding this entire block. So in the worst case, we will end up and adding uh, how many elements. So if I say that I have divided my array into k blocks, then each block will roughly have, or at max can have n by k, sorry, n by k elements, right? So this how many elements do each block have? Sorry, how many elements are present in each block? N by k. So in the worst case, I will be adding up n by k elements to answer my query, and this will be done twice for BL as well as for BR. So let me add some constant c over here, but that does not matter. What in the so now we understand why this term k plus n by k is important, because k over here is a variable which denotes how many blocks we have. All right, and if we want to, so this is basically the time complexity that we are going to spend this much amount of time on answering each query, and there are q number of queries. Alright, there are q number of queries where q is nothing but 2 into 10 to the power 5, which we have already seen. Okay, so in this case, to optimize, what is the minimum value of this particular expression? It's nothing but root n, right? And root n will come when value of k is equal to root n. So for best purpose, we define our k as nothing but root n in order to solve this particular question in q into root n complexity. So this particular problem using square root decomposition will be solved in order of q into square root n time complexity. All right, and what is this? 2 into 10 to the power 5. This is nothing but 2 into 10 to the power 5, and square root of n, where n also belongs to 2 into 10 to the power 5, is nothing but 20 into 10 to the power 4, and square root of 20 is nothing but somewhere around, well, let's upper bound it with 5, and 10 to the power 4 is nothing but 10 to the power 2. So this brings down the complexity to 7, oh sorry, 7, 10 to the power 8. All right, so this is doable in the given time frame. Okay, so in the next part we will code this particular approach, and thank you for staying this till the end, and I hope you get the clarity of the square root decomposition algorithm, and let us meet in the next part where we will code this out.